It's a great pleasure to have Omri Solan, who will tell us about gap in critical exponent.
Great. So I want gap in critical exponent is a big spoiler to my talk, but I'll start to give you a more delicate and slightly less spoiler. So in my talk, I will talk about actions of SL2R. Acting on a space X. And what I'll be interested in is I take a point X inside X, and I want to study the stabilizer in SL2R of X. Of beta X. So if the stabilizer is a lattice, the orbit is SL2R of X. It's called periodic, and in many cases, periodic orbits have been studied quite a lot. But today I want to ask a different question. What can you say on the stabilizer if it's not a lattice? So in general, we cannot say anything, but I'm not going to talk on general. I'm going to talk on a very specific space X. I'm going to be interested in a very specific points, collection of points, little x inside big X, and I'm going to say something on the stabilizer, and you can guess from the talk it's going to be something on its critical exponent. I'll explain what critical exponent is. So the first thing is space X. Second is the little x. Third, what we want on stabilizer for white stone. Okay.
Could you please write in such big bigger letters or something? Difficult to read.
Yeah. Okay. 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 So the space X will be related to the following space. There is a space SL2R. SL2R of real matrices with determinant 1 mod SL2Z. So this space is studied a lot, and it's equal to lattices lambda inside R squared with determinant 1. Okay, and now and a different perspective to this space is if we take a lattice lambda and relate it to the torus R2 mod lambda. Now this is a torus, and we can think of a torus as a parallelogram. When we identify the opposite edges, and let's draw with a different color. Okay, so SL2R mod SL2Z is the space of parallelograms. I'll write only para because I don't know how to write parallelogram. Parallelogram with vol 1, but when I glue with glue. Larger, sorry. Let's try.
Parallelepiped.
I think it's parallelogram or it,
Dimension two is fine. Yeah. I'm just saying, if you went to 3 dimensions, what you gonna call
okay.
it?
So tori are genus 1 surfaces. What happens if you want larger surfaces? Then we can still write, okay, now I have it. We can still take a polygon, say this octagon, and identify this edge with this edge, this edge with this edge, this edge with this edge, and this edge with this edge. And we have a polygon when we identified the two opposite edges. When we had opposite edges that are parallel and of the same length, and when we wrote this identification, we got a surface that almost everywhere it's flat. It looks like R2, but at one point at this vertex, it's not flat, and in fact it has 6 pi degrees. If we try to track what is this point, we go around here, and then we live here, and the point this is this, and it goes here, and here, and here, and here, and I missed something. No, now we've got here, and here, and here, and go back. And altogether, if we went around this point, and we went 6 pi degrees because every octagon, the sum of the degrees of the angles is 6 pi. So we have a polygon. When we glue certain edges, we got a surface with genus 2. And for me, I'll have it will be the same if I cut this blue line and identify this polygon with, and I glue now this part in the edge that is glue, and it's the same surface because it's the same. When now I glue, let's write here this and all the other edges that you can see here, here. I got the same surface. So here we had genus 2 surface, and it had one point with more than 2 pi degrees, which was any of the vertices. I can make other polygons, say this square. In this square, we'll get it. This point is same as this point, and this point, and this, and this. And we have this point, this point, this point. This point is this point. And so we have 2 special points. Each of the special point has 4 pi degrees. 4 pi, as each point has the sum of the angles around it is 4 pi. Okay, and so just like here, we had a certain space that was parallelograms when we glue opposite edges. We can study the space of all surfaces that are obtained by gluing edges of polygons. So I write H of K1 up to Km. That's going to be space of glued polygons. But now I want K1 and Km to describe this special point with more than 2 pi degrees around it, with special points, special I don't remember how special. Points P1 up to Pm with Pi has 2 pi times Ki plus 1 degrees around it. Okay, so now this polygon represents a surface in H2 because it had 6 pi degrees around this point, and this polygon is inside H11 because it has 2 points, and we can count, and each one of these points has 4 pi degrees, 4 pi radians around it. Okay, so we have the space. In SL2R or SL2Z, we had a volume 1 assumption, and we want to assume it here as well. Space of glued polygons. Okay. So now we have a space of glued polygons, and we can act on it using SL2R. Using real matrices, we can act on R2, and so we can act on each polygon, and we can just multiply it by any matrix and get a new polygon. So it take the octagon, this octagon, and I'll act on it using the matrix 1101, which does something like that. Then it is gonna skew, but then I can cut it because I want it to be more compact. I don't have to cut it, but I can. And I take this part and move it to here, and now it's like that. When this edge is glued to this edge, the blue is glued to the blue, and so on. And so, and this is the space. And okay, the volume is preserved. The angle pattern is also preserved. Angles are not preserved by multiplication by matrices, but how much time you rotate around the point does preserve. And this is my space X and the action on the space that I promised. Are there any questions on this space? Okay, so we have the space of flat. This is called the space of flat surfaces because surfaces with some that are flat. Okay. So before I tell you what orbits I care about on these surfaces, I'll tell you a few. I'll try to motivate the dynamical action on X. What happens on these dynamics? So one thing that is common in dynamics is to study invariant measures and ergodic measures. So the first thing I want to tell you on these spaces is the theorem of Eskin and Mirzahani. They more or less classified invariant measures, and they show that all maybe that's not the first I want to tell you about. Sorry. Okay. So I'll finish my sentence. All ergodic measures, all ergodic invariant measures.
For SL2, not for the Borel.
For SL2, for the entire action. All ergodic SL2R invariant probability measures are Lebesgue. I write only Lebesgue. Are Lebesgue on submanifolds. So all ergodic and invariant measures are very nice. They are Lebesgue measures on certain submanifolds of HK1 to Kn. But before that, I want to tell you a bit on before this statement. I want to tell you something about the space HK1 to Kn. So first, it is a manifold. Up to some, if you treat it right, it is a manifold of dimension 2G plus m minus 1 times 2. Okay, maybe I write it here. Has dimension 2G plus m minus 1 times 2 minus 1. So it's a manifold with this dimension.
What is G?
Okay, G is the genus of the space, which can be expressed using K1 to Kn. Gauss-Bonnet says that G equals sum 2G equals sum 2G minus 2 equals sum I. And
He knows what genus is better than anybody. It's a genus of the flat surface.
yeah, so 2G minus 2 is the sum of Ki's. So yeah. Okay, and the first thing that I want to say is that there is a certain Lebesgue measure on the space. Exists lambda h k1 up to km, which is Lebesgue on h, which is Lebesgue, and it is SL2 invariant and this is a theorem of Kmazor and Fitch. And usually the measure is called the Mazur-Fitch measure. So we have an ergodic and invariant Lebesgue measure on the entire manifold, but also it turns out that all invariant and ergodic measures are Lebesgue. Okay. So I'll tell you a bit more on this dynamics. So we studied Lebesgue, we studied ergodic measures. Now I want to study invariant closed sets. So Eskin, Mirzakhani, and Mohammadi showed that all invariant closed sets in H K1 to Km are finite union manifold. And these manifolds are the same manifold on which the Lebesgue measures are the ergodic ones. And an important part of the proof of this result is a crucial ingredient of Eskin, Mirzakhani, Mohammadi's proof is that any sequence, any limit of invariant and ergodic measures is ergodic. So if we study the space of ergodic measures, then it's closed. If we take a weak star limit of ergodic measures, then the limit is again ergodic. In the proof, there was a certain argument that shows that. So due to Eskin-Mirzakhani, to prove this result, you only need to eliminate to show that a measure the limit is supposed on a single manifold, and for that you need to somehow avoid other manifolds. I don't want to go too deep into the proof. That's all I want to say about it. I want to leave this line here. Okay, that's what I want to say in general. But now we care about orbits.
They also, I forget the order, but they also study the Borel invariant measures.
Yeah.
In connection.
Actually, I mean, just they talk about, they classify the Borel invariant measure, not the asymptotic
Yeah.
measures.
And then this,
I think there was even a stationarity assumption you could assume, not the entire invariant. Okay.
Borel subgroup, that is. Not Borel.
Yeah.
Two Borels.
Okay. Okay. This is something very general, but let's talk on orbits. How can we make a closed orbit, a periodic orbit? So a way to make a periodic orbit is if you assume that all the coordinates of the points are rational, then there is a common denominator. Let's call the denominator if points rational. So exists denominator 1 over, and if the denominator is 1 over q, we can project every point in the manifold mod 1 over q, and we define a map from S to a torus, a tiny torus, 1 over q on 1 over q. And this torus is, we can define such a map. And if we act, so this is a covering map, it's not exactly covering map, above any point, it is as the covering map should satisfy, a discrete collection of points, but over 0, all the points with more than 2 pi degrees fall on 0. So it's a very special map. And if we act using SL2Z, this map is preserved. We can act on with SL2Z on S and with SL2Z on the torus. And this
SL2R.
We can act using SL2R on both sides. But if we act using SL2Z, the torus goes to itself. And since there are only finitely many such covering maps, there is a finite index subgroup of SL2Z that stabilizes S. And so if points in Z, the stabilizer in SL2R of S is a lattice. Okay, so we can ask, are these all the examples for lattice orbits? And I'll give 2 results of McMullen. Okay, in H1, in H2, and McMullen, and this is also Kalta. Okay, in H2, no, the more orbits, the infinitely many more, no, exists infinitely many irrational orbits, rational periodic orbits. However, this is a theorem only of McMullen. In H11, only one irrational period, only one. So it turns out that in H11 there is one periodic orbit which is irrational, and that's it. Okay, so that's
So those are, I assume, some Veitch surfaces.
Yeah, these are Veitch surfaces.
These surfaces and periodic orbits are sort of synonyms.
Same thing, right?
Veitch surface is an orbit, is a point whose orbit is periodic.
So, like the pentagon is in which one of those?
I think it's the only, the pentagon is this unique one. Okay, so we talked about periodic orbits, but in my spoiler, I wanted to talk about non-periodic orbits. And so this is another theorem of McMullen. Suppose B is a rational number and greater than 0. And A equals B minus 1 plus square root B squared minus B.
So, by the way, in the other case where the infinitely, where the ones which are coming from your subgroups of SL to Z, they thought of mostly non-congruence, because, right?
I believe they are non-congruents. I don't.
They'll have a deck group, yeah, which kind of a big homology, yeah.
Okay, so we take B to be a rational number, B minus 1 plus some square root of something, and we want it not to be a rational number. And now we can talk on this polygon, so that this square is a square of side 1, this square is 1 plus A, and this square is A. So in this case, McMullen showed that, so if this is SA, so it has no volume which is greater than 1, we can normalize it to have volume 1, that really doesn't matter, but the stabilizer in SL2 of SA is not a lattice, not a lattice, but is infinitely generated. It's a discrete subgroup, which is probably Zariski dense. I think it's not a lattice, infinitely generated, Zariski dense in SL2. For those who know, the limit set of this group is everything. It doesn't matter for this talk, but yeah, so this is the stabilizer. This is the point they want to study that interests me, and this is the stabilizer they want to study. Yeah, so it's really hard to say something on the stabilizer. How can you somehow identify? So in McMullen's proof, goes something like that. McMullen identified certain points from certain geodesics that start from one. He studied geodesics that start from one special point to the other. Say something like that.
So these are geodesics in the flat matrix.
Yeah, geodesics in a flat matrix in this space, maybe goes from one to another. And there are two, and he showed that for infinitely many geodesics, if you act on this space using the matrix using unipotent matrices that preserves this direction, then in some cases, he exactly specified in which cases the unipotent action that preserves the green direction is periodic, and when you flow in this direction enough, you actually get the same surface after some time. And he showed that in other cases, he showed that this is exactly not the case. He started in the same one. So I don't know. Yeah. If in other cases, he showed that in a positive proportion of the closed geodesics, it is periodic, and positive proportion of the closed geodesics. It's not periodic, and the infinitely many parts, infinitely many closed geodesics that closes that are periodic give you the infinitely many generators, and the non-periodicity gives you the not a lattice phenomenon. So being able to identify some elements give you very little power on how to control the group. Yet I want to say something to prove you something on this group. So what do I want to say on this group?
You're talking about the stabilizer.
Oh, the stabilizer, yeah.
The discrete subgroup of SL,
Yeah,
which you say has full dimension for the limits.
yeah. It has the limit set is everything.
We need to be careful. It's an infinitely generated group, so one needs to be a bit careful about how.
Yeah, maybe it's interesting the limit set. So I want to study it in terms of critical exponent, as you had as in the title. Let me define critical exponent.
Why you guys are worried about the limit set? I guess is it because it's tangential or non-tangential, that sort of thing? Yeah, okay. All right. Yeah, I don't like infinitely generated groups.
Sorry.
No, I'm used to it. So I would not think of the subtle distinction.
Yeah. Okay, so the way we want to control groups is discrete groups. So suppose lambda inside SL2R is a discrete subgroup. Okay, so we can intersect lambda with a ball. Take lambda intersect with a ball of radius R. And now we can, the volume of the ball of radius R is grows exponentially, grows e to the R with the right metric. And the intersection, and if lambda is not somewhat simple, if it is risky dense, then this intersection grows exponentially. The size of this, the growth rate of this intersection is exponential. And so we can count how many points, take a logarithm, divide by R, and take a limit.
Okay, so this kind of Patterson-Sullivan theory doesn't apply in terms of the relation between the limit set and the critical exponent. That's what you're keeping away from. Okay.
Yeah, so now we have, and this is the critical exponent.
Commutator subgroup is
I know it's a lot like that, yeah.
favorite.
It is not.
So the critical exponent is,
Well, you always pass to a finite index. Finite.
okay, so for lattices, if lambda was a lattice, the growth rate of this intersection was roughly the growth rate of the volume of the ball. And the growth rate of the volume of the ball is e to the R. And so taking logarithm divided by R, taking limit, we get 1. And so if lambda lattice, the delta of lambda is 1. If lambda is Zariski dense, then the critical exponent is positive. As Peter said, the limit set of lambda, the dimension of the limit set of lambda is the critical exponent if lambda is finitely generated, but not in general. And this is an example that it's false. Okay. Let me give
It's also too crude to see things like there are examples that grow like e to the R over R, where there's some over powers of R, so that will get washed out.
Yeah, here we don't see that. Yeah, but the bounds you'll give is
You can distinguish between lattice and Zika, or sort of.
if you take a finite index subgroup that is not finite index, a normal subgroup, so the quotient is a billion. The critical exponent doesn't say that.
That's
Okay,
the case where you get R to a power.
let me give a different characterization. You said some dimension of limit set. That's not the characterization that I want to tell you about. I want to characterize it in terms of probability invariant measures. Invariant measures on SL2R mod lambda. So if mu is a probability invariant measure on SL2R mod lambda, invariant with respect to, okay, that's a good question. Let's write A of t equals e to the t over 2, e to the minus t over 2. This is a matrix that this ball was chosen so that this matrix has exactly size t. And so the entropy, so here we have A invariant, and I want to say that the supremum over mu of the entropy with respect to mu of A1 equals the critical exponent. That is the characterization.
It's been a long time since I looked at Sullivan's work, but did he not still show that if you take the radial limit set, then it's that Hausdorff dimension, or is it?
So-
He's got some fix up with the radial limit set, right?
I don't know. I'm not that familiar. I found what I needed, and that's
Okay. All right.
uh,
I think he
you
fixed
can
it.
show there is okay. This inequality is fairly simple. It's not complicated to see that the entropy is a lower bound of the critical exponent, and its equality in finitely generated subgroups. And Sullivan showed that that delta of lambda is the supremum of finitely generated subgroups of the critical exponent of the finitely generated group, and that's how you show this equality.
I think he did carry on to talk about the radial limit set as replacing the regular limit set. And somehow things got back to normal, so to speak. In other words, the relation between the dimension. But maybe it's got some other assumption.
Okay. So now we know the critical exponent. And my question was, what is the critical exponent of this stabilizer? What can I say about it? And so that's the goal of today. Okay. The theorem gives a bound on the critical exponent of these points, but in fact, for every k1 up to km and every x inside, okay, there exists epsilon. So that for every x inside h k1 up to km, for any flat orbit, one of the following holds. Either SL2R of x is periodic. So either an orbit is periodic, or the critical exponent of the stabilizer in SL2R x is less than 1 minus epsilon.
Exists epsilon.
There exists epsilon, which depends only on k1 up to km. If you take maximum, depends only on the genus. That give me an upper bound on this critical exponent.
How's this related to the mixing rates at Avila and Co?
It's not related very much. I think that part of the proof you can see things that will be related, but not.
So you don't give any estimates for the exponent?
Yeah, that's a good question. Epsilon is absolutely, it's mysterious.
Effective.
It's ineffective. I show the proof is somewhat in contradiction, and I use certain I use in this proof, I use Eskin-Mirzahani Muhammadi, and if that's not effective,
Yeah.
I cannot effectivize this one. So, yeah.
But is this some analog of the Phillips-Sarnak dimension bound, and is that one way to think about this?
It seems much deeper. This is, I mean, it is about a lot, yeah, so if you have Schottky groups, then there's a universal bound for the dimension. So you take supremum of all finitely generated Schottky groups, then in dimension 2, Doyle completed this, gave a universal bound for the dimension, which would be a similar theorem. But they're not coming from this.
Right, of course.
non-linear.
But is it somehow analogous?
I don't know, I haven't seen
I mean,
this.
it's not a theorem
If
about,
I gave you an effective version of the Eskin, the Hani theorem,
You'd have to
you would not
effectivize,
be able to effectivize this epsilon.
you'd have to effectivize quite a few results in the middle. So that you have any chance.
But in SL2C, where you have effective everything, you don't know how to effectivize this epsilon.
Yeah. Okay. So,
in connection with Alex's question, you could say, well, the way you've set it up, you're saying that groups that come through this Teichmuller dynamics, or whatever this thing, this flat surface, you have a gap, and then for Schottky, you have a gap. There may be some, it's not like you're proving a theorem about gamma, it's really related to Mirzakhani very closely in Eskin, right?
yeah, it's okay. There is a method the method is somewhat involved. You can, many parts of the method are completely one part of the method is completely general.
For any discrete group.
In some setting, it's more general as I present it, but you'll see exactly what is what is general here and what really relies on Eskin-Mirzahani.
Not just Eskin-Mirzahani. It's not just Eskin-Mirzahani. It's also there's more delicate things of Wright, Philip, and Eskin. It's a delicate.
Yeah, but it's only in this dynamics here.
It's sort of.
It's not about so much the lattice.
That's already not so much dynamics in my book. This Philip Wright Eskin.
Okay, we mentioned Philip Wright Eskin, and I want to first, before I show you how to prove this, I want to give a guess as to how they would prove where it is here. So McMullen showed that in H11 there is only one periodic orbit. I want to hint about I want to somehow show a different way to show if there are only finitely many of those. Okay. So the proof that I give is based on, has ideas from Eskin, Philip Wright, and okay, so let me assume to the contrary. Assume there exists xi I from 1 to infinity. So inside H11, so that SL2 xi are all periodic. So that's the assumption. That's an assumption. So now the first thing we can do.
So they'll be distinct from one another.
Yeah, are all distinct. Okay. So let's take the invariant measures on these orbits. If they're periodic, there is an invariant measure. Mu I invariant, SL2R invariant. SL2R invariant on SL2R. Okay. So the first thing we can do with a sequence of measures is study equidistribution. And this is a sequence of invariant ergodic measures on H11. Then, if you remember this part of the proof of S linear Zerhani Mohammadi, we said that limits of invariant ergodic measure are again ergodic. So limit of mu I is ergodic. So it's Lebesgue on some manifold. Let's assume that this manifold is everything, is H11.
This is ergodic probably this with more values.
Yeah. Limit mu I is ergodic enhance lambda is H11. There are more options. There are more invariant ergodic options, but let's assume this assumption here. Okay, but that is possible. I haven't constructed a contradiction, and I cannot. I cannot construct a contradiction because I forgot one assumption. I forgot to use the irrationality of the orbits. If I don't use it, how can I prove anything? So I need to are distinct, periodic, irrational. Okay, so I need to use somehow the rationality of these orbits. And now, I don't need this anymore. If a certain polytope, all the vertices are rational, so you can consider the group generated by these vectors, and this group would be a rank 2 discrete subgroup of R2, because it's rank 2 discrete subgroup of Q2. It's a discrete subgroup inside Q2. It's a finitely generated subgroup inside Q2, and those are all cannot be with more than rank 2. So to use the rationality, I want to tell you that a certain group has larger rank than 2. That would be my irrationality criterion. Okay. So, but studying the group generated by these vertices is not something really well defined. I can cut and glue it otherwise, and it will not be exactly. It's not exactly well defined. So let me define it slightly better. So if I want to define you these vertices, what I actually want to study is the homology of the manifold H1 of S. So if I have a manifold, a flat surface S, and they have any class in the homology, let's do it in green. Okay, now it sounds here. They can study how much this curve, this cycle in the homology went. So it went in this vector and then this and then this. Then I have this total displacement map that for any curve that for any curve you define an element in the homology, it gives me a two-dimensional vector that studies how the sum of this, the total displacement of this curve, the integral of the derivative. So you get a map that's called the period map from the homology group of S to R2. Does this make sense? But I still cannot capture, I wanted to capture all the vectors, all the edges, and edges are not necessarily elements in the homology, because this point and this point are not, maybe not the same point. Here they are, but in general, they don't have to be. So instead of H1, I want to do something relative to the singular points, the points with more than 2 pi degrees, singular points Now I put here real. Okay, and now I actually get the image is exactly what is generated by all the edges. So, so this is the claim for any S inside H11 periodic and irrational. The period group, the period map of H1 of S with coefficients in, not coefficients, relative to homology, relative to the singular points, is rank 4. So maybe we should, so the homology itself is rank 4. The relative homology, now it's the relative with respect to the two singular points that we have in H1, was added 1 to the rank. So the relative homology is of rank 5, and the image of the relative is of rank 4. So that's the ranks. Before before you say that this sounds weird, I don't really care for periodic orbits. All I care for is these orbits. These orbits. And here you can really see that the group generated by edges generated rank 4 thing, because the x coordinate and the y coordinate are both in what generated by, in the field generated by A. So it's in QA squared, and that's rank 4. So maybe this claim is weird in general, but in our case, it holds. Okay, so now we can use this and consider the kernel of a period map, which is a rank 1 subgroup inside the homology. So kernel of the period map is rank 1 inside the relative homology. Relative homology is of rank 1. Okay, so now we have our space H1, and above every point we considered this homology, this relative homology, and you got a rank 5 bundle. And above every point in our orbit, we got a one-dimensional subgroup. And so if we consider the projective bundle of this bundle, projectivization of H1 rel S is now relative to the singular points with coefficients in R, we get a projective bundle with a section, and give a projective bundle with a section. Okay. So now, if we take our measures UI, so we had our orbits SL2R xi, they were inside H11, and there was a section to a projective bundle above H11. So if we take the limit of mu I, but now we not embed this orbit inside, we don't think of this orbit inside H11, but we embed these measures in the projective bundle, we still get a limit of measures. And the limit will be SL2R invariant, and we get an SL2R invariant measure on P that projects to Lebesgue on H11. And now, theorem Epstein really right? There is no SL2R invariant measures until P projects to lambda H11. Okay, so that is the proof via Eskin-Philip-Wright. But it doesn't show anything about the critical exponent. So now,
Eskin-Philip-Wright. Finiteness of finiteness results for each surfaces.
yeah. So they didn't wrote exactly that. If you'd take what they wrote, it won't be this proof.
Philip will be here next week, we'll ask him.
I won't be here next week.
Okay.
But I mean, okay, but that's why they were sort of looking at these things, because they were into understanding the finiteness properties of surfaces, etc.
Yes, the result is much more general than what I presented. Don't let me.
I mean, you running between the case of genus 2 and McMullen in general, which McMullen was using, if I remember, Jacobians and Ratner in his classification, right?
Yeah.
You're not using that, right?
No.
Okay, okay.
I'm using this Eskin-Philip-Wright and Eskin-Mizrahi and Eskin-Mizrahi. Okay. So what do we do if
Yeah, your theorem is general, anyway.
my theorem is general? It's not.
Nothing to do with that.
It's not only on H1. So what do we do if we now don't have it? They're all periodic. We have it, the critical exponent of the stabilizer. Maybe I want.
Sorry, for H11, you said that there's one non-periodic
There's one
Any proving finite.
non-periodic irrational.
direction.
And here I only prove finiteness. Because if there are infinitely many, then some limit will be bad. So now let's assume to the contrary that there are infinitely many orbits. SL2 are
If
xi.
there's finitely many, then you know, oh, you don't know that delta is strictly less than one for each of them.
Yeah,
Okay.
maybe there is one for all of them, but then the sequence of orbits will be just the constant orbit of one fixed orbit. But let me write in general delta of the stabilizer. So sequence of orbits, delta of stabilizer goes to 1. That's the assumption that we need to disprove. If this happens, then it means assume that xi are of this form, exactly of this form. Okay, now the critical exponent of the stabilizer go to 1. Then by this characterization of the critical exponent, it's a supernorm of certain entropies. So let's ui on SL2R times SL2R times xi AT invariant and the entropy with respect to mu I of H1 goes to 1. So we have the limit of the entropies is the same as the limit of the critical exponent is 1. So now we would like to implement the very same strategy. So the first thing we need to do is to show that the limit is certain, is Lebesgue on some affine measure. So now we have the limit of the entropies goes to 1. So and in dynamics there is some general strategy that if the limit of the entropies is the entropy of maximal, is the entropy of measures maximal entropy, then the limit of the measures is what you want. But here the entropy is only 1. It goes to 1, but the space is more than the expanding horse. The expanding horse is more than one-dimensional, and only on SL2R you can get one dimension. But you know that all the entropy is in the SL2R direction. And so And so the first thing you want to show is that the limit is SL2R invariant. And that's what you can hope to get, because that's what the entropy somehow it lives, all the entropy lives in SL2R direction. And so you can hope to get some invariance in SL2R. Okay. And that's the main technical, that's the main part. If mu on SL2R mod lambda has H mu, okay, is AT invariant and let's say ergodic and H mu of A1 is greater than 1 minus epsilon, then mu is epsilon SL2R invariant. So for any lambda, for any discrete subgroup lambda and any measure on this quotient, any AT invariant that has a large entropy is almost in SL2R invariant. That's my theorem. And now
That's a general statement.
that's a general statement. It's more general for measures.
No, I don't understand the statement.
I didn't define epsilon invariance, so it's
No, when my measures are on a space, on a big space, I don't understand what's happening here.
you have here a quotient of SL2R.
Lambda is, you're saying any discrete subgroup.
Lambda is any discrete subgroup. And you have any measure on discrete subgroup is on this quotient. It is AT invariant.
But I mean, that's not the situation you have. You have a measure on space which you sort of have, and then you want to reduce it to SL2R invariant. I mean, you don't have.
I know, but what I have are measures on orbits. And here and each orbit is isomorphic to a quotient of SL2R or lambda. And so it's an equivalent situation. And here I get that the measures are epsilon SL2R invariant. They're in some sense very close to be SL2R invariant. And now when we apply it here to measures mu I on H1, the limit will be SL2R invariant. And now we want to show that it's indeed ergodic, and this similar ideas from Eskin. So you'd have to adapt where it is. I think it's behind the board. No, yeah, it's probably behind the board. You'd have to adapt Eskin Zahani Mamadi, but you would get it. And so you get that this limit is ergodic. Let's assume the invariant on H1. And also you could take the limit, you'd have the same sections to the same projective bundle because on this space, the periods were all inside to the QA squared. And so you could construct the same bundle, the same sections, take the new measures and lift them to P, and take the limits there. And you would also get this, that the entropy implies extra invariance, and this theorem would give you a contradiction. Yeah.
So this becomes very difficult.
No, not actually.
It's sort of the main.
It's the main thing. It's okay.
It's not the way you presented it to me sometimes. That's the way of looking at it. It's sort of a strange definition. What would be this epsilon SL2 invariance is probably not what you would guess first, because these measures are very much not SL2R invariant.
They're not invariant, but you still can for any G, you can find if you take mu and G mu and G mu and mu, then you can find a joining between mu and g mu that are very close. That the average of the distance is little of 1, as depending on epsilon. That's not the way it's written in the paper. I agree.
To me, it looks very clean, because in fact, you could imagine other situations where you have maximal uniqueness of maximal entropy built in something. Found you get a gap. Same way. I mean, you kind of pull it. This separates out the Teichmuller part from the.
Yeah, this is nothing to do with Teichmuller.
Right.
It can be stated.
There's still some things to say, because one of the things you need, which is sort of, you want to show that your periodic growth become a good, not periodic, these measures mu I become a good distributor.
Yeah, you need.
That's not a formal statement. I mean, okay.
No, I'm not saying the reduction is.
So you need to somehow do some version of Eskin. You need to check that the Eskin Mirzahani Mohammadi would work also. If you loosen these assumptions, I mean, that's sort of, it's not that this takes care of everything. I mean, it's somehow, this is one step that you sort of, there are other things that we need to do.
There is a big technical part. Big.
I mean, you're showing one place where you quantify.
It's in this version, it's not really quantifiable, but
No, not quantify. I mean, where the limit, where you get your epsilon.
yeah.
So this is. That's it. It is a gap. It's not a gap in the proof, I hope.
Yes.
I'm sorry, I don't know if this is sort of ignorant, but is there any version of this for p-adics?
Of the Teichmuller space, of the flat surfaces thing. I don't know.
Probably you know better than us, I can somehow.
If you go to the character
This kind
variable,
of modular spaces, people probably look at them, I mean, right? Over the periodic numbers.
I guess some of the things you can. So
this is
the Teichmuller space is an algebraic object, but the action we induce on it is a very non-algebraic action. It actually takes the holomorphic structures through it.
I mean, this work, say in this certain cases, very closely related to Mirzakhani counting mapping. So this Teichmuller dynamics can be used to count Markov triples or something like this. And in that case, you certainly have a p-adic theory, because all those varieties are defined over the integers. And then the dynamics, then you look at the dynamics, and it's very, that's exactly what we're doing. That's what what's the name was talking about 2 weeks ago. Ali Resin. I mean, there is this work of, yeah, but that's more in Thurston style work, not in this Beach Mesa direction, as far as I know.
This Eskin right theorem is general for because your statement is for general H.
My statement is for general H, and you need to actually look at what they really proved. They classified, they showed that there is a certain group that is attached to each bundle, and they computed it. And if the group has no fixed vector, fixed measure, then the bundle has no invariant measure. It's yeah, I can state afterwards the exact.
There must be a relation to the gap in the exponential mixing of the SL2R action that they study. Yeah, you don't know any relation?
Again, I mean, you could look at the case which I understand better what happened if you look at portions of SL2C. If you look at SL2C modulo non-arithmetic lattice, and then you could look at orbits of SL2R where the stabilizer is Zarinsky depth. So there, okay, I know. I don't see a relationship. I mean, I would like. This is something which I would like to have. I mean, I would very much like to have some kind of way I can say that the gap. It depends. This gap is a dimension. It depends on the spectral gap for
this fixing, yeah.
for this thing. But this is something which surely should be true. But it's not something we know. So,
No, but I mean, it does reflect some kind of uniform gap.
it would be. I mean, you could dream that that gap should be somehow reflected here, but it's also the argument doesn't give any relation.
Okay, but that's what I'm dreaming.
You could hope for that, and even it's not okay. It's not really.
I mean, I remember Forney lecturing here some years ago and saying that maybe somebody, one of those fellows, has a kind of that something is tempered under some conditions. You know what this conjecture?
Yeah, I know what tempered is.
No, that it's some kind of tempered. And people have asked in that context for uniform spectral gaps. I'm very interested in, of course, having that. In that sense.
Spectral gaps are interesting in when you have a uniform family of things with spectral gaps. Yes.
So as far as I know, you should look on these measures and study these measures on SL2 on the space, and they may be very singular. And if there is no equidistribution, they are very singular, and so I don't know how to control this very singular measure with anything that is defined on the deck measure and everything.
How general is this thing, this 5 and 4 thing? That's sort of how it works also in the general case, or that's also
Yes, it's exact. So in general, it can be.
It's not going to be 5 and 4, but that's sort of roughly how it goes, or?
It's roughly how it goes, yeah. There is. So here he defined a one-dimensional thing. It's worth noting that this one-dimensional object, that there is a three-dimensional subspace inside this H1, that this one-dimensional thing only lives inside a three-dimensional bundle. Everything that is so the kernel lives in the bundle of all the forms that if you look on the real homology, then the kernel of the integral period lives in the kernel of the real period map and the kernel of the real period map is a three-dimensional object inside the five-dimensional, because when you consider the period over the reals, it's mapped from a five-dimensional object to a two-dimensional object, and so its kernel is three-dimensional. And so you need to consider actually a three-dimensional object, and this three-dimensional object, and you should work in the dual, in the cohomology, and then it's some two-dimensional inside the section inside the three-dimensional bundle. And there is some structure that I'm hiding from you, and it's all hidden inside this Eskin-Philip Wright, but the structure is very similar. It's very general, and it works for almost every case, but not all of the cases. H2, it's still here. In H2, this argument doesn't work, and you need to, and there is another argument that you need to apply in H2. It's completely different, not ergodic argument. In manifolds, it look like H2. Yeah.
in your theorem that you had earlier about being epsilon close. How general is that? Like, change the group essence bar.
What is your definition of epsilon in that would be a good start before we discuss how general it is.
Okay, I write here epsilon invariant. There is a function delta of epsilon, maybe not delta, no, zeta of epsilon that goes to 0 as epsilon go to 0. Okay, maybe.
You're in the right, so just next to you.
Okay. Okay, for every G inside epsilon to R, there exists zeta, the zeta G epsilon. So zeta. Okay, what I'm saying is not a version that it's not what's written in the paper. And
I mean, it's you could discuss, you could say something different. When you have some kind of you have the unstable, there's a distinguished direction, which is the top Lyapunov direction. You can sort of look at the entropy that you have this distinguished direction. If it's almost maximal, then in the limit you get something that's sort of going to be invariant in that direction. That's sort of the version of the argument that I understood.
okay, let me write a different formulation that is much easier to write and easier to explain. Somewhat more
At
formal.
some point, we need to allow people who
Okay, then I'll finish
allow
this.
people to sketch it somehow.
I'll finish this zeta G of epsilon that goes to 0 as epsilon goes to 0. And so that if you take mu and G mu, there is a joining, then mu and G mu, there is a joining between mu and G mu that, so that for every, so that if you take the average of the distance of point here and the point here.
It's not invariant under A, so I don't understand what joining means.
Both mu and G mu are measures on the same space. And you can take just the probability joining, not an invariant joining, not just the probability joining, a way to sample one point here and one point here that are close, that the average of the distance of the minimum between the distances one is less than zeta G.
So it's like a Wasserstein distance or something between.
Yeah, I think that's the name. Yeah. There is it's written in more explicit and somewhat not exactly equivalent way in my paper, in the paper, but it's, yeah, but I can show it afterwards.
Looks to me like we should thank the speaker again.